Chapter 13, Section 10 is on Lagrange multipliers. The method of Lagrange multipliers is named after the French mathematician Lagrange first introduced the method in his famous paper on mechanics when he was just 19 years old. Our objectives are to understand this method and use this method to solve constraint optimization problems, and as well as use this method with two constraints. Many optimization problems have restrictions or constraints. One such example that we did in section 13.9 was the optimization problem. We were asked to find the dimensions of the rectangular package of largest volume such that the sum of the perimeters of the two cross-sections could not exceed 144 inches. The volume was what we were trying to maximize, and the constraint was that the sum of the two perimeters of the cross-sections cannot exceed 144. So that's an example of a problem with a constraint. In this section, you'll study an ingenious technique for solving such problems, and it's called the method of Lagrange multipliers. Now, suppose you want to find the rectangle of maximum area that can be inscribed in the ellipse given by x squared over 3 squared plus y squared over 4 squared equals 1. Here's a sketch of that ellipse and an example of a rectangle that can be inscribed in that ellipse. Our goal here is to maximize the area of that rectangle, and the constraint is that the points of the vertices of the rectangle have to be on the ellipse. So our objective function is what we're trying to maximize is the area of this pink shaded rectangle. Now, if there's a point on the ellipse with coordinates x, y, then the area of just this portion in the first quadrant is the length times the width, or x times y. And since there are 4 of those little smaller pink rectangles that add up to one large rectangle, we see that our function that we're trying to maximize is 4xy. That's the total area of that pink shaded box, pink shaded rectangle that's inscribed in that ellipse. And again, the constraint is that the point has to be on the ellipse that satisfies this equation. In using the method of Lagrange multipliers, we're looking at finding the level curves of our objective function that just satisfies the constraint. The constraint is the ellipse. That's two-dimensional. Our objective function, what we're trying to maximize, is a function of two variables, so you can think of that as three-dimensional. One way to represent that three-dimensional surface is by graphing the contour lines or the level curves. So when you're sketching the level curves, it works out that the level curve that just touches that ellipse is going to help us find the solution to the rectangle with the largest area. So we want to find out where those just touch. And it just so happens, since they are tangent at that point, the gradient of the constraint function is going to be parallel to the gradient of the level curve. So we're looking at the scenario where the gradient of the f of xy function, that's the gradient of the objective function, is going to be parallel to the gradient of the constraint function. So if it's parallel, then it's equal to some scalar multiple of the gradient of the constraint function. So in this, we are using the symbol to denote that scalar for the Lagrange multiplier. So theorem 13.9 is Lagrange's theorem. Suppose you have f and g must have continuous partial derivatives such that f has an extremum at the point x sub 0, y sub 0 on the smooth curve g of xy equals c. If the gradient does not equal 0, then we could say there's a real number lambda, that's the Greek lowercase letter lambda, such that the gradient at the point of the original objective function is equal to some scalar multiple of the gradient of the constraint function. And that scalar multiple is your lambda. That's what we call the Lagrange multiplier. Now, the method of Lagrange multipliers is found by solving the equations where the gradient of the f of xy function is equal to that multiplier of the gradient of the g of xy function. Again, f of xy is what you're trying to maximize or minimize, and g of xy is equal to a constant. That's your constraint equation. So if these gradients are equal, then the partial derivatives with respect to x and y, if these gradients are parallel, then the partial derivatives with respect to x and y are um, scalar multiples. So this is how we get this system of equations. The partial derivative with respect to x of the primary function, f of xy, is equal to that multiplier times the partial derivative with respect to x of the constraint equation. And the partial derivative with respect to y is equal to the multiplier times the partial derivative of that constraint with respect to y. And also we need to consider the constraint equation itself. So we should end up with three equations. And you want to evaluate the original function at each solution obtained in the first step when you solve these systems simultaneously. The largest value is going to yield the maximum, and the smallest value is going to yield the minimum, subject to the constraint. In this example, we're going to use the Lagrange multiplier with one constraint. Find the maximum value of f of xy equals 4xy. That's the area of the rectangle that's inscribed in the ellipse, where x is greater than 0, y is greater than 0, and it's subject to the constraint that is the equation of the ellipse. So we are going to find the f of xy function, the gradient of that, as well as the gradient of the constraint function. Now, if we're letting this constraint function be our g of xy, so the gradient of our f of xy function is found by taking the partial derivative with respect to x, that's your 4y, and the partial derivative of this with respect to y is your 4x. So this is the gradient of our f of xy function, what we're trying to maximize. And the gradient of the g of xy function is going to be the partial derivative of this with respect to x, that's going to be 2 over 9x. The partial derivative of this with respect to y, which would be 2 over 16y, or y over 16. And we're going to multiply that gradient by that Lagrange multiplier, that lambda. So we get our equations for the gradient and lambda, the gradient of f and lambda times the gradient of g. So from these two equations, you can say the partial derivative here, the I component here has to equal the I component here, and the j component here has to equal the j component there. So we can say that 4y has to equal 2 over 9 lambda x, and 4x has to equal 1 over 8 lambda y. So here we have a system of equations. We've got two equations with three variables. So to have a complete system, we need one other equation, and that's going to end up being the constraint equation. Again, our constraint equation is the equation of the ellipse. Now, from the first equation, going back, we want to solve, if we solve for lambda, okay, take the first equation and solve for lambda, we can divide both sides by 2 over 9x. We get lambda is equal to 18y divided by x. And then when you substitute this lambda into the second equation, we get 4x equals 1 over 8, 18y over x times y. We can simplify this equation by dividing by 4 as well as multiplying by x, and we get the equation x squared is equal to 9 over 16y squared. Now you can take what x squared equals here and you can plug it into the constraint equation. You're dealing with three equations and three unknowns. So this is a method of using algebra to solve the system of equations. Again, if you plug that in using the first two equations by combining those, solving for lambda and plugging it into the second equation, you get this. And then when you substitute that into the constraint equation, you get this. So this ends up simplifying to 1 over 16y squared plus another 1 over 16y squared equals 1. And that gives you 1 over 16 plus 1 over 16 is 2 over 16, or 1 over 8 times y squared equals 1, or y squared is equal to 8. You can solve this for y by taking the square root of both sides. And the square root of 8 is plus or minus 2 square root of 2. Now, because it is required that y is greater than 0, we're going to choose the positive value. Now, if you know what the y is, go back to this equation we found by combining equations 1 and 2. Plug in the value you found for y and simplify to get x. So we're plugging in that square root of 8 and simplifying. So x squared is 9 over 2. So that means x is equal to 3 over the square root of 2. So you have a value for x and a value for y. So the maximum value is what you get when you evaluate that primary equation, that objective equation, by plugging in 3 over square root of 2 for x and 2 square root of 2 for y into the equation for the area of the rectangle, which is 4xy. When you plug those in and you simplify, you get that that area is equal to 24. So that ends up being the rectangle with the largest area that can be inscribed in that ellipse. We used gradients and the method of Lagrange multipliers to solve this optimization problem with a constraint. In the next video, I'll be going over some examples, minimizing functions given constraints. Here is one such example. Here's another example that we'll be looking at, minimizing this function with given this constraint equation using the method of Lagrange multipliers. And then we're also going to do this example of finding 3 integers whose product is 125 with a minimum sum, another type of optimization problem with a constraint.